Welcome to using differentials to approximate function values. So for an example, let's go ahead and approximate the square root of 9.2 without using a calculator. So we know that the square root of 9 is equal to 3. And so what we're going to do is we're going to set f of x equal to the square root of x. And then we're working with x equals 3 and we're working with x equals 9, and then we have a change in x of 0.2. So we're going to set change in x, which is our dx, equal to 9.2 minus 9, otherwise known as 0.2. So let's go ahead and find dy. For x equaling, sorry, I keep writing 3, x equaling 9, and dx equal to 0.2. I didn't give myself enough room once again. So the first thing we need to do is just find the general equation for dy. So we know, so we need to find f prime of x. Again, recall that if f of x is square root x, that's the same as x to the 1/2. So f prime of x would be equal to 1/2 times x to the negative 1/2. Or f prime of x is equal to 1/2 times the square root x. So we have the generic formula for dy is f prime of x times dx, or 1/2 times the square root of x times dx. And then we have, so this is our dy. And then we can plug in x equals 9 and dx equals 0.2. So we are looking at this dy is now 1/2 times the square root of 9. And then that whole thing multiplied by 0.2. And this becomes 1/2 times 3 is 6 times 0.2, or 1/5. And 1/6 times 1/5 is 1/30. From there, we can go ahead and approximate f of 9.2. And how we will do that is f of 9.2 will be equal to f of 9 plus the change in y, which is going to be approximately f of 9 plus dy. And f of 9 is the square root of 9, which is 3. And dy we just found to be 1/30. So we have that f of 9.2 is approximately 3 1/30, otherwise known as 3.033 repeating. So again, what we're doing is that change in y is the actual change from f of 9 to f of 9.2. We're approximating that change in y by finding dy. And then we can just do f of 9 plus the change in y is the actual value of f of 9.2. Using the approximation dy, we do f of 9 plus dy, and we get a reasonable approximation. So let's go ahead and do one more example. So again, we want to approximate sine of 0.25. So we know that sine of 0 is equal to 0. And then we'll set the change in x equal to dx to be 0.25, our new x value, minus the known 0. So the 0.25 is coming from what we're trying to approximate. The 0 comes from the one that we know. So we're setting dx to be 0.25. Again, we'll set change in y to be, before we do that, let's set f of x to be sine of x. And then we'll set change in y to be f of x plus change in x, or x plus dx, minus f of x. And then again, we have f of x plus dx, if we just rearrange this, should be equal to f of x plus change in y. So this is what we were using earlier. And then this is going to be approximately equal to f of x plus dy. So we need to know the relevant x value we're working with is 0, dx is 0.25, and we need to find dy. So we have x is going to be equal to 0, dx is equal to 0.25, and we need to find dy. So again, first thing we need to do is find f prime of x. So f of x was sine of x. Derivative of sine of x is cosine of x. Then we find dy. And so we have dy is equal to cosine of x times dx. Once we have that, then we can go ahead and plug in x equals 0 and dx equals 0.25. So we have dy is equal to cosine of 0 times 0.25. Cosine of 0 is 1. So we have 1 times 0.25, or simply 0.25 is our dy. So now we will go ahead and approximate sine of 0.25. So using what we had earlier, sine of 0.25 should be approximately sine of 0 plus our dy. And so we have sine of 0 is 0, plus dy was 0.25. And so we are going to approximate sine of 0.25 is approximately 0.25. Now this is likely not going to be accurate. And sine is at its steepest right at 0, but it curves down. So this will be an overestimate. But it does give us a reasonable approximation and a quick way of approximating sine of 0.25 if we do not have a calculator available.